thank the organizer for organizing this event. It's important for us to remember Christoph and to share our memories. I'm very grateful for that, and also for giving me the honor to invite me. So I met Christoph probably the first time at a memorable Les Houches school in 1984, where I also met some of the people in the audience. It was a great experience. And then I was postdoc at IHES, and we discussed a lot with Christoph, and he had a very strong influence on my personal development as a scientist, but also as a person. I mean, he gave this example of a very integer person, which I appreciated very much. So at that time, we started to discuss about strings and conformal field theory, and also quantum groups, which will be the subject of my talk. And it was, so I learned a lot from him. He had this very vast knowledge of mathematics and physics, and he was always eager to explain. And it was a very stimulating time for me, and at times a little frustrating, because by the time I would start to understand the question and imagine some answers, he would come up with a very precise and complete answer, often in the form of this manuscript that Denis showed last time, very precise, very complete, and there was nothing much to do after that. So, and I also liked his dry style and almost cynical style on his comments on science. And I remember once I was unsure about whether I had some small results, and I was unsure about whether they were worth publishing or something. So I asked him for advice, and his answer was very short: you should first publish and then think whether it is worthwhile publishing or not. Right. Okay, so today I will talk about Howe duality, which is a generalization of Schur-Weyl duality and the connection with dynamical Weyl group. So this we came to this duality by studying some formulas, fermionic formulas for R-matrices. I will mention that later, for Fock spaces. And so it started with a master thesis of Rea Dalipi, who was a master student at ETH, and now she's a PhD student in Geneva. Okay, so let me see if this works. Okay, so this is a plan of my talk. I will review this very classical by now Howe duality between GLN and GLM, and I will then explain how we arrived at this in these fermionic formulas for R-matrices of exterior powers of vector representations. And then I will explain the connection with the dynamical Weyl group, and we have some small improvement on the results of Etingof Varchenko on that dynamical Weyl group. And I will explain then some other limits of these results in the quantum Weyl group, the B operators, and the Youngian limit. So I will talk about the quantum affine case, and then there is a rational limit, which is the limit of Youngians. Okay, so let us start from a very basic story about Schur-Weyl duality. So if you think about the symmetric group Sm of permutation of M letters, then you see that it appears in two different ways in the representation theory of the general linear groups. So for the purpose of this talk, let me call these two sides of the appearance of the symmetric group, the Schur side and the Weyl side. So the Schur side will be the following. So suppose you have a representation W of the general linear group, for instance, the vector representation. This is a classical setting. Then you can take its nth tensor power, W, tensor W, and so on. And then you can act with the symmetric group on this tensor power by permuting the factor of the tensor product. And so this action of the symmetric group commutes with the diagonal GLN action on the tensor product, and which is a starting point of the Schur-Weyl duality, because they are, the images are commutants of each other. If you reduce one into irreducible representation, you already reduce also for the other group into irreducible representation. So this is a very classical story. And what is the other role of the symmetric group? Well, the symmetric group is a subgroup of the general linear group. You just take permutation matrices with 1 and zeros. And this, let me call it the Weyl side, because it is a Weyl group of GLN. And so it acts on any representation of GLM. Okay, so on one side you have GLN, and the other side you have GLM. Okay. So, and this story has also a quantum version, very well known by now. But there you have to replace the symmetric group by the Braid group, or sometimes the Hecke algebra, but the Braid group in general. So you consider the Braid group with m strands. So it's an extension of the symmetric group, and it appears on two different sides, again of the representation theory, but now of the universal enveloping algebra of GLN. I will of the quantum universal enveloping algebra of GLN. I will review what that is in a second. And namely, you have again a Schur side and a Weyl side. On the Schur side, you again take tensor powers of any representation W of, actually it should be UQ of GLN. And now UQ of GLN is a Hopf algebra, which means that you can act on tensor product of representations. But it's no longer true that permuting the factors commutes with the action of UQ of GLN. But as Jimbo noticed in 1986, this action commutes with an action of the Braid group instead of the symmetric group. In the vector representation, it factors through the Hecke algebra, but basically it is a Braid group which plays a role here. And again, there is also a Weyl side. You can ask, can I, if I have a representation of my UQ of GLM, say, is there some analog of the action of the symmetric group? And again, there is an action of the Braid group, which is called the quantum Weyl group. This was done by Lewandowski, Seubelman, Lustig in the 90s, around 90. And so you have a parallel story, but the action of the symmetric group is replaced by the Weyl group. Sorry, by the Braid group. Okay, but what we are interested in is a quantum affine version, which is, if you like, a version with parameters. So where these parameters come from, it is when you go from the representation theory of GLN or UQ of GLN to the loop algebra. So you have a loop parameter instead. And this is before quantum groups. This story appeared in statistical mechanics, namely with this R-matrices, the Young-Baxter equation. So what is a Schur side? We have this R-matrices with spectral parameter now. So, and here there is this little stupid thing, but which plays an important role here. So there are kind of two versions of it. There are the R-matrices and the braiding matrices. And they differ by the composition of permutation of factors. So today it will be mostly about the braiding matrix. So anyway, we have these braiding matrices with spectral parameter, depend on a spectral parameter, and they are solutions of the Young-Baxter equation from statistical mechanics. This is an old story, and it was kind of the beginning of the theory of quantum groups, but it appeared before. Namely, you have this relation here. So this R matrix is an endomorphism of W tensor W for some vector space W. And if you consider triple tensor products, then you can consider these two sides, and the Yang-Baxter equation says that they are equal. So, so this appears in, you can take matrix elements of these R matrices as Boltzmann weights for some statistical models, and from these relations you deduce kind of integrability, commuting transfer matrices, and so on. So this is a very classical story in exactly solvable model in statistical mechanics. And so, but one kind of representation theory formulation of this is to say that these R matrices, or these braiding matrices more precisely, provide a representation of the symmetric group on functions of M variables with values in this tensor power. So it works like this, that it's sufficient to give the action of generators, the transposition of neighboring letters, and this transposition act on a function with values in the tensor power of W. In this way, you act with your braiding matrix on the ith and I plus first tensor factor, and you replace the spectral parameter by the ratio of these two functions.
What is
Lowercase w, maybe. It's a complex number, yes. The spectral parameter. So the Yang-Baxter equation has two parameters. So for all z and w, you have this identity in the Yang-Baxter equation, yes.
Should there be w?
Yeah, probably there is a misprint, yes. There is a w on the left side instead of a z. Yeah, thank you. Right, so, but, so here you see that the braid group is again replaced by the symmetric group, but now we act on functions of n variables. And you can reproduce the braiding matrix that appeared in Jimbo, for instance, in the limit where z goes to infinity or to 0. And then you have constant braiding matrices, and you can reproduce. But you see that there is this inversion or unitarity relation. Maybe I should point it. So if you send like z and w to 0, then you get some identity of braiding matrices. But of course, you have this relation here. So if you send z to 0, then z inverse goes to infinity. So this is lost in the limit where the spectral parameter goes to 0 or infinity. And that's why you go from symmetric group to braid group. Okay. So this is the Schur side, and then you can ask, what is there a Weyl side also, some representation on for a given representation of your affine Lie algebra, quantum affine Lie algebra, is there an action of the symmetric group depending on parameters? And this is more recent. This was done first by Tarasov, Varchenko, and then in a paper by Etingof, Varchenko around 2001. So you have an action of the braid group on v-valued functions of M. So now the variables, for some reason, are called dynamical variables. So you have, again, functions of M variables, and taking value in a finite dimensional representation of UQ of GLM, or maybe the loop algebra, actually, we'll see. And it's called dynamical Weyl group action. So it is constructed out of intertwining operators and so on. I will not review that part because we will propose a different construction of this dynamical Weyl group. But again, there is a version of this quantum Weyl group of Lustig depending on parameters, like the spectral parameter in the theory. Okay, so, and in the suitable limit of these dynamical variables, we get the quantum Weyl group of Lewandowski, Seubelman, Lustig. Okay, so we will propose a different interpretation and an extension of the result of Tarasov, Etingof, and Varchenko. based on this Howe duality. So let me now review this Howe duality. So here what you consider is is GLN and GLM. So you have the vector representation, C to the n of GLN. And now, so now you can act with GLN and GLM on this exterior algebra of the tensor product. And so again, it's like in Schur-Weyl, you have that the images of the actions are each other's commutant. So again, you have a representation, the representation of GLN and GLM of these two commuting actions can be decomposed in irreducible representations. So they look like this. So a direct sum. So this is the notation for highest weight or irreducible representation of GLN, and here GLM acts. So as you know, the algebraic representation of GLN are labeled by partitions or Young diagrams. And so GLN has, the representation of GLN are given by Young diagrams with at most n rows, and GLM with m rows. So here you take the transposition of your partition or Young diagram. You transpose your Young diagram. So you sum actually over all partitions which fit in an m by m square. So then it's consistent. And right. So this is the classical duality, and I will come back to this duality in more detail. So when we started to see these formulas of R-matrices, we looked, I didn't know about this Howe, so we started to look in the literature. And I think the first reference we found was a paper of C.N. Yang and Zhang. In 1970, they were looking at the Hubbard model and noticed that there is some SO4 hidden symmetry in the Hubbard model. And if you think of it, it is if you have a system of fermions, so so it would be the case where you have n would be the number of sides and m would be equal to 2. So because every spin has every fermion has 2 spin states on some lattice, and so they were seeing some action like this. And then we saw that Howe had this duality, and then actually in this Q case, it was at least implicitly in some older paper of Constant in the 60s. So there is a symmetric version and a skew version. Today we'll consider the skew version. Okay, so let me explain a little in more detail how this works. So how to do that? So let's V be C to the n, W C to the m. So now so this is basis depends. So you have your standard basis. So you can write V, well, maybe so the wedge should be removed here. So you can write V tensor W without you shouldn't read this wedge here. So V tensor W can be written as V plus V plus V plus V. And so if you take the exterior power, then you can write it in this way, right? And so you have an isomorphism between this exterior power and the tensor product of exterior power. But you can also do it in the other way by taking the basis, standard basis in Cn, and you get it like this. So on the left, it is clear how to act with GLN, and on the right, so here you have m factors, and each V is a representation of GLN. And here it is clear how to act with GLM. Okay, so this is how this action works, and the claim is that these two actions commute. So we have m factors, and also the other remark is that you can use the GLM action to select the exterior power, namely, so you look at the left side, you have a tensor product of exterior algebras of this representation of GLN, And now, if you look at the weights for GLM, the action of the diagonal matrices of GLM, the eigenspaces are the exterior powers of these representations. So it's a weight subspace of weight K1 up to Km for the GLM action. And so in particular, if you take the weight 1, 1, 1, you get first exterior power, namely you take V tensor V tensor V tensor V, and here this reproduces the classical Schur-Weyl duality. You have the tensor product of vector representations, and now the subgroup of GLM which preserves this weight space is given by permutation matrices. So you have an action of SM on this weight space. And so, right. So it's one way to understand the Schur-Weyl duality. So this Howe duality also has a generalization to the quantum case. So we have the Drinfeld-Jimbo again, a quantum enveloping algebra with the deformation parameter Q. And so the first observation is that these exterior powers can be directly defined also for the quantum group, namely, so the classical relation of these roots, simple roots generators, is deformed to that one. And now you have what is called the minuscule representation. So this, in the exterior algebra, or exterior powers of the vector representation, this HI have eigenvalue 0, 1, or -1. So this quantum deformation does not play a role. So this Q to the H and so on is equal to H if the eigenvalues are 0, 1, or -1. So you can just take the same, so this one construction of the exterior power, you just take the usual exterior power and you act with the generators like in the classical case. There is another construction using quantum kind of exterior power, but this is one possibility. Okay, so and so the features of the quantum groups appear where you start to take tensor products of such representations. Okay, so what is a quantum skew Howe duality? So one version is, so it's known, it was done by these people. So I think the symmetric case, it was known earlier, but the skew symmetric case was done by these people. And so in one formulation, it looks like that. Again, you take a tensor product of such exterior algebras. You, again, decompose V tensor W as a direct sum of V plus B plus V. You get these two isomorphisms of vector spaces. And then on the left, you act with UQ of GLN using the coproduct. It's a Hopf algebra. And on the right, you use GLM. And the claim is that they commute. And again, we have this decomposition like in the classical case into tensor product of irreducible representations. So it's very similar to the classical case. And now we would like to go to the quantum loop algebra. So, so the loop algebra would be Laurent polynomials with coefficient in GLN, or if you like, Fourier polynomials. So they admit a Hopf algebra deformations, which is obtained from the affine Lie algebra by setting the central element to be trivial. And so it contains the constant loops, the UQ of GLN as a Hopf subalgebra. And also you have the spectral parameter, which comes from the fact that you have this one parameter group of automorphisms, namely, so which in the undeformed case is just the rescaling of this loop parameter. And so if we twist the representation by this automorphism, you get new representations depending on parameters. That's the point here. So, so now we have an action of UQ of GLN on this, and it extends to an action of GLN by simple formulas, essentially the classical formulas. And then you can twist by this phi of z, and you get a representation, which is called wedge v of z, parameterized by the spectral parameter, or evaluation point. And so the thing is that if the spectral parameters are generic, then the tensor product is irreducible. And also the two orders of the tensor products are isomorphism as representation, but the isomorphism is a non-trivial object, and it is this braiding matrix or composition, and which is the isomorphism. And since the tensor product is irreducible, as it is for generic parameters, then this braiding matrix is uniquely defined up to normalization. And so one abstract way to get it is to use the universal R-matrix of the quantum affine algebra composed with a permutation of factor, and you get this matrix. But from that point of view, it's not clear that it's an infinite sum. It does not clear that it converges, and indeed, it does not always converge. So for certain special value of z and z prime, there are singularities of this matrix. So, okay, so this is our object of interest, this R matrix, which again, as I explained before, would give a representation of the symmetric group on functions of the spectral parameter. Okay, so now, so this is a little slide on this loop algebra. So there are generators and relations. Maybe I will not say much about it. So you have this deformation. So I now, what I called q to the hi, I now call ki. So, and you want to go from SLN to GLN, so you introduce this ti, which correspond to kind of diagonal matrices in GLN. Okay, so we have these generators, EI, Fi, which is useful to think of to be in Z mod NZ, 0 to n minus 1. And if you leave out the zeros generator, you get the UQ of GLN, the kind of finite dimensional version. And so the automorphism can be defined by scaling this additional generator E0 and F0 by Z or Z inverse, respectively. Okay, so this is the story. And you have a formula for the coproduct. Okay, that's not so important. Okay, so of course, this braiding matrix was described explicitly in the 90s by Dato and Ocado. And what they do is they use, if you like, this decomposition into irreducible representations for GLN, for the finite dimensional UQ of GLN. And so it's a finite sum. And so in each of these sub-representations, it acts as a scalar. And they computed this scalar using the fusion procedure of Reshetkin and others. And but we would like to give a fermionic formula for that, which is kind of more explicit. And we want to exploit this Howe duality. So how to exploit the Howe duality. So we have this R check, which is a homomorphism of modules. So it must come, since we know that the two, so now we have two, we have the R-matrix, we have a tensor product of two exterior powers. And so we have the GLM, dual GLM is a GL2. So on this tensor power, we have a commuting action of UQ of GL2. And since we have a homomorphism of modules, it must come from an action of an element of the Howe dual UQ of GL2. And so which it is, and it is given, by, turns out, by nice formulas if you use these fermionic operators, as C.N. Yang would do in his description of the Hubbard model. So we view this exterior algebra, so direct sum of all these exterior powers, as a Fock representation of fermionic commutation relations. So this is the usual kind of Clifford algebra. So this exterior power, or exterior algebra, the whole direct sum, is a representation of the Clifford algebra with these generators. And these are the canonical commutation relations. And it's generated by a vacuum vector, which is the zeroth exterior power, if you like, which is killed by the annihilation operator psi I. And then you can act with psi I star to build up your representation. Okay, and then there is also this, map from UQ of GLN to Cn. So you can represent your loop algebra by these fermions. And so it's given by quadratic expressions in these fermionic generators. This is a kind of classical story. So the EI are such quadratic expressions, and then the kind of Cartan elements, which are Q to something, are Q to the number operators of fermions. You can write it in this way. So this is one construction of these representations of UQ of LGLN, of the quantum loop algebra. You map it to the Clifford algebra, and then you act by these fermionic operators. So this was done by Ozono in 1990. But then it's also useful to describe this dual UQ of GLM action in terms of fermions. And actually, the theorem that I mentioned before of kind of the quantum version of the Howe duality is most easily proved if you use these fermionic representations. And so the action is also conveniently expressed in fermionic operators. And for us, so this can be done in general, but for us, for these braiding matrices, the m equal 2 again case is important. And so let me use capital letters to denote the action of the dual Howe dual group. So we have capital E, capital F, the standard generators of UQ of GL2, and T1, T2 are the diagonal elements. And so they act in this way, again, quadratic expressions. But here you have to use this coproduct, or maybe the opposite coproduct. Maybe I didn't say that. So in this Howe duality, on one side you use a coproduct, on the other the opposite coproduct. So you have these formulas, these explicit formulas for generators, for the action of generators. And again, so you have to select the case exterior power in this tensor product, and K prime, which is we want to do. You have to take the weight space of this UQ of GL2 dual action of weight KK prime. So namely, these generators T1 and T2 act by Q to the K prime and Q to the K and to the K prime. Okay, so now the statement of Howe duality is that these operators again act and obey these relations. And so now there is a nice universal formula for the R-matrix by the action of this dual UQ of GL2. And so for this, let me use this divided power notation. So this E to the parenthesis L is L's power divided by the Q factorial. This is just to simplify the formula. And then we want to normalize the braiding matrix so that on the highest weight vectors, it is -1 to the KK prime to spare some signs in the formulas. And then we have this kind of explicit formula for the R matrix. So the R matrix on the tensor product is given by the action of an element of UQ of GL2, which is given this kind of explicit formula. And so what are the features of this formula? So one thing is that this gives kind of it's a sum of terms, kind of one new feature of this formula is that it's a sum of terms, and each has a simple pole. So this gives some kind of interpretation of the residue of the simple pole. And the other one is that in some sense it is independent of capital N, right? Because it's given by this dual construction. And so it also works in the Fock space representation. So if you take the limit n goes to infinity, you get R-matrices for Fock spaces. So this was actually the starting point of our discussion. Maybe it is written here. Right. So this was kind of inspired by a paper of Andrei Smirnov, who gave some formulas for Fock spaces given in terms of fermions, but for the Youngian. And so I will discuss that. So, but that formula was for R matrices, and here we have braiding matrices. I will discuss that again. And so now maybe the question is, now we have this representation of our braiding matrices as an action of these dual objects, these elements of UQ of GL2. And now, of course, we know the R matrices, as we saw, obey Yang-Baxter equation, inversion relations. So there should be similar identities for these elements of UQ of GL2. So what are they? And so if you think of it, so the Yang-Baxter equation, for instance, is an equation in the triple tensor product of representation. So from the point of view of Howe duality, in this triple product, we have an action of UQ of GL3, right? And so, for instance, the Yang-Baxter equation involves these three tensor powers, three tensor factors. And so the identity for this AM, for these elements of UQ of GL2, corresponds to embedding of UQ of GL2 in UQ of GL3. And this you can do in two different ways. You can embed as kind of, it's like embedding GL2 in GL3. You can take it as an upper left 2 by 2 matrices or lower right 2 by 2 matrices, among others, right? And these are the two embeddings corresponding to the simple roots. And indeed, we have two embeddings of UQ of GL2 in UQ of GL3 corresponding to simple roots. And so more generally, you can ask what happens if I have m factors, m tensor factors. Each of them is an exterior algebra. There you have an action, as we saw, of UQ of GLM, if you have m factors. And you have m embeddings of UQ of GL2. And now, so there you have more weight. So we have these elements A, I, mu. I is the number of the simple root. Mu is a weight of GLM. And now you can embed it in a natural way, these elements of UQ of GL2, depending on a weight, a GL2 weight, to elements of a SLM weight or GLM weight in UQ of GLM. And now the claim is that you have these relations here, which are actually basically the relations of these dynamical Weyl groups. So then we can forget about the fact that we obtain those elements of UQ of GL2 from tensor product of exterior powers. We have just elements of UQ of GL2. We can embed them in UQ of GLM or even generally algebras. And then we have these identities, which are the identities of kind of dynamical Weyl group. So for the GLM case, we have this, that if we have I and J are far apart, we have this relation here. Then we have the inversion relation, which can be written in this way. And this would be the analog of the Yang-Baxter equation. And this now takes place, instead of a tensor product, it takes place in the endomorphisms of a fixed representation of GLM. So we have a representation U of GLM. It has a weight decomposition. U mu would be the weight space of weight mu. And then we have these identities, which are basically, except from the point 2, are the 1 and 3 are the relations of the quantum, or the quantum dynamical Weyl group. Okay, so now we have, for each weight space, we have some operator, and now we can take them together. We have this AI of U, which are on each weight space is given by this embedding of UQ of GL2 with some weight related to mu. And so if you have any, I don't know, integrable or finite dimensional representation of UQ GLM, of type 1 means that doesn't matter. So the endomorphisms of UQ define a representation of the symmetric group. So this is this formulation of quantum Weyl group. So now there is here a little small discrepancy. So it's basically the dynamical Weyl group, but there is a slight discrepancy with the original definitions. So the generators of the dynamical Weyl group of Etingof, Tarasov, and Varchenko are defined by similar formulas, but they do not obey the inversion relation 2. So you remember that we started with a symmetric group, then we went to the quantum case, we got the Braid group, and then to the quantum affine case, we recovered the symmetric group by acting on functions. And it turns out that our formulas are related to the formula of Etingof, Tarasov, and Varchenko by multiplying by scalar functions of these dynamical variables. And so our claim is that by multiplying by these functions, we recover the symmetric group out of the Weyl group. Instead of the Braid group. And so their kind of representation was a representation of the symmetric group only if you restrict to the zero weight space of a representation, and ours is on the whole space. Okay. And and by construction, we start from R-matrices with inversion relation, so we get also the inversion relation in the quantum dynamical Weyl group. Again, so the limit, when z goes to infinity, you get the Braid group, the quantum Braid group, and so we get this quantum Weyl group in the limit. And now, so there is a question, the relation between this braiding matrix and the R matrix. So in the rational case, for both we have nice formulas. Smirnov wrote some of them, but in this case we need to go to the B operator. So this is, instead of multiplying to relate the braiding matrix to the R matrix, instead of multiplying by the permutational factor, we multiply by the limit of the braiding matrix in the limit as a spectral parameter, or dynamical parameter goes to 0, and we get the so-called B operators, which are endomorphism, and they are given by nice formulas. In the rational limit, they reproduce the R matrices, but otherwise we have these matrices here. Okay, it doesn't matter so much how they look like, but it is interesting to look at the rational limit, because those Lustig matrices converge to the just permutation of factors. Okay, so this is the rational limit. Maybe I will rush through it and so on. And in this rational limit, you will get solution of Yang-Baxter equation corresponding to the Yangian. And so, and in the limit, you can go from the braiding matrix to the R matrix, and then you get some formulas which were, at least, it's a version of the formulas that Smirnov was writing. So this would be given by this formula here. And here you have, in the rational limit, you have simpler formula for these generators, which in terms of fermions. Okay, thank you for your attention.
Did it ever matter whether Q was a root of unity or a general value?
Most of it still works. So the identities still work for Q root of unity. What doesn't work is this kind of decomposition into irreducible representations. That's more subtle. But
yeah. Okay.
There is this geometric approach to the R-matrices, I guess with dynamical R-matrices, we're coming from the study of K-theory of some varieties, in which the R-matrix comes as actually it's derived object, so there is a more basic object called stable envelope, and then iteration of two stable envelopes. So your formulas do seem to have kind of a triangle structure. You have a product of F's on the right, E's on the left. Do you have any geometric interpretation of that?
I'm not sure. So, so the kind of the geometric construction was a motivation of this work, and because also Smirnov was considering it. So this should be some version of three-dimensional mirror symmetry, right? So, but because you have kind of relate stable envelopes for some Nakajima variety to some kind of dual variety. So I think it could be interpreted in that way, but I don't have details at the moment.
Yes, I have a question about Q operators. So you are not talking about them, but what would be the consequences of those dualities on the Baxter-Q relations?
Right. Yeah, I haven't thought about that. Right. So Q operators for exterior powers, right? Yeah, I don't have an answer. Thank you for the question. I think it's an interesting question.
There is also another question about, well, you know, in the standard, most simple representation, there is this notion of Drinfeld twist.
Of, sorry?
Drinfeld twist.
Which twist, sorry?
Well, you can decompose, the twist is relating the standard coproduct to the deformed coproduct, right?
Ah, okay.
So do you have some hints there? What happens to such twists in these duality relations? Can you, for the more complicated R-matrices that you showed? Right,
but what kind of, so let me see, so you twist the coproduct?
Well, it's decomposition of the R-matrix as a twist in the, well, Cartan and then inverse twist with the exchange factors.
Right, yeah, no, I haven't thought about it.
Okay.